Hi everyone, welcome to this is day 28 of Math 133. So we are at the end. Today we're going to cover the Chapter 11 review, and this is the last of our material. So there's no lecture notes. The final exam covers chapters 1 through 11. So once we've done this, you guys will be an expert in statistics. Uh, we're going to cover the Chapter 11 review, which starts on page 563. And it's 6 pages, so make sure you grab all 6 pages. Page 563. Um, on Tuesday next week, we're going to cover the sample final exam. Also on Monday and Wednesday, Cindy and Elaine are going to cover some of the sample final exam with you. Um, and the final exam is next week. So it's next week on December 11th if you're taking it with me on Zoom. Just like with the midterm, if you're taking it on Zoom, we're going to have 3 hours. So we're going to start at 6 p.m. and we'll go until 9 p.m. Okay. That's if you're taking it in the evening. If you're taking it in the morning session, we're going to start at 9 a.m. and we'll go until noon. Okay. So the midterm was 9 pages. The final exam is 12. Okay. So if you were running out of time on the midterm, you should seriously consider taking it at the testing center. The testing center, you can take it Tuesday through Friday next week. So Tuesday, Wednesday, Thursday, or Friday next week. And if you are taking it on Friday, December 12th, their hours are a little shorter. I think it's 10 to 2 maybe. Still plenty of time, but make sure that you set up an appointment because since it is less hours, I don't want you to miss out, okay? Definitely don't miss taking the final. If you didn't get a chance to, so if you're watching this on Zoom and sorry, on the video, if you're watching this on the recording and you weren't able to come to class, make sure you fill out the discussion board. Today is the last discussion board. There's no discussion board for next week. Okay. I'm going to be sending out a survey, so be on the lookout for that, asking where you're planning on taking the final exam, uh, whether you're taking it with me or not. It's just so we know how many copies to print at the testing center. It's no big deal if you change your mind, but it's helpful to know. So be on the lookout for that. Um, yeah, so let's jump in to the Chapter 11 review on page 563. Okay. Um, if you click on the Chapter 11 review in Canvas, there's going to be a link that's going to take you to the data sets for today in StatCrunch. So when you click on that link, it's going to take you to this list of all of the different StatCrunch um, work set or worksheet reviews and stuff like that. So if you click on this link here in StatCrunch, I'll drop this in the chat so you don't have to go hunt for it. So this is our data that we're going to be going over today. So I'll put that in the chat for you. Okay. Um, and honestly, this is not that many numbers. So if you needed to, you could just open a blank StatCrunch and just fill in the numbers that way. Okay. So, okay, but we are going to be on page 563. Okay. And I'm going to go through, give you some hints on a couple different things, and then we'll go back through and we'll finish all the stuff we skipped over, okay? Um, so, uh, in 2024, 40% of adults in Michigan, 38% in Wisconsin identified as Republican. You want to conduct a study to find if the difference in these percentages have changed. So it's been almost 2 years. Have these numbers gone up or down? So to do that study, you need to know how many people you're going to need to ask. So how big is your sample size? How many adults in Michigan and Wisconsin must you sample to correctly gauge the difference with 95% confidence within a 3.2% margin of error? So you need to show your formula and then do some substitution. And then what's your result? Okay. So page 261 has the sample size formula. So up here is if you have a single population. We have a double population because we're looking at Michigan and Wisconsin. So we're going to write out our formula, okay? So depending on whether we have a prior estimate or not. So here in this case, these are what the numbers were back in 2024. So that's our prior estimate. And now we're checking to see what's the sample, what's the number now, okay? So we're going to use this one. So you're going to write that out, put in the numbers here, and then get your result. Now, when you do your result, make sure you specify that that result is for both states. It's how many people you need for Michigan and how many you need for Wisconsin, okay? You can't just sample a little from this and a little from that, okay? So page 261 at the bottom. All right. Question number 2, how many adults in Michigan and Wisconsin must you sample to correctly gauge the difference in the percentage of residents that believe in astrology with 99% confidence, 2.4% margin of error? So again, show the formula, do the substitution, and get your result, okay? And for this one, I know it's Michigan and Wisconsin for both of these questions, but they're not related. So you can't say, oh, well, these people are Republicans, so they must believe in astrology. So yeah, this case, we have no prior estimate, okay? Because they didn't give us any. I don't have any guess what percent of people believe in astrology. Is it I would hope I think it's probably less than 50%, but I don't know. So we're going to use the no prior estimate. Okay. All right. A researcher carried out different two-tailed hypothesis tests. So they did 4 different studies, looks like. Which of these studies is associated with the smallest p-value? Okay. So remember, so these are z values. Okay. So z values are on this x-axis here, or z-axis, or whatever you want to call it. Okay. So 0 is right here. So if you're very close to 0, so if you're like 0.01, you're going to be shading a huge part of this curve. And the part you shade is how much your p-value is. And actually, this is a two-tailed test. So over here is negative 0.01, which you're going to be shading like this whole thing, okay? So if your number is close to 0, you have a very large p-value, okay? Hopefully that makes sense. All right, circle true or false after each statement. Explain why. So type 1 errors are always worse than type 2 errors. True or false, guys? What do you think?
False.
False, right? So it depends on the context. Depends on what you're studying. Okay. We've already seen cases where type 1 might be worse or type 2 might be worse. Okay. We saw where type 2 was worse if we were looking at like COVID vaccines, and uh, a type 2 error was where your null hypothesis was false, and or COVID tests. It was COVID tests, not vaccines. COVID tests where the test said you're fine, and you went out and you got people sick, and that was no good. Okay. But we saw another one where type 1 was worse, where if we put a piece of we installed parts in a jet airplane that were weaker than the old parts, and so you would end up possibly causing plane crashes, right? So now that was in chapter 10, but even in chapter 11, it depends on the context. Sometimes type 1 is worse, sometimes type 2. Um, and sometimes they both suck. So, yeah, anyway. Um, let's go to the next page. New post-surgical treatment for a common surgery with thousands of patients a year is being considered with is being compared with the standard treatment. 7 random patients receive the new treatment, 7 random patients receive the standard treatment. Here are the recovery times in days. So recovery time is how long it takes until you're, back up on your feet and leave the hospital, go home, right? So they're asking us to find the sample size, the mean, the standard deviation for both of these. So to find a standard deviation, we had 3 methods on page 254, and we're just going to use method 1. You use method 1 on this one and method 1 on this one, okay? So you'll find this data in that StatCrunch link that I dropped in the chat, okay? Or you could just type it in. It's only 7 numbers here, 7 numbers here, so it's only 14 numbers, so it's not that long to just type them out. But on page 254, we go to stat, summary stat, columns, right? And then select the things you want. For the standard one, compute that, okay? All right. Verify the conditions necessary to construct a confidence interval of the difference in recovery times. So we need to make sure it's random, okay? And then here we have 2 different samples, okay? So we need to check that the samples are either dependent or independent, okay? Depending on whether you have an independent sampling or dependent sampling, okay? So how do you know the difference? So, and that's going to be important because here we're looking at trying to figure out the average recovery time, right? So page 265 and page 266 are similar. Page 265 is the test for the mean of matched pairs. Okay, so we're testing means, which is what we're doing for this problem, matched pairs. Here, when we're checking our requirements, we check to make sure they are dependent samples. Okay, in other words, one group measured twice. Okay, page 266 is where we are looking at the test for difference between 2 independent means. So independent or dependent. And here we look to make sure that the samples are independent of each other, which means we're checking to make sure it's 2 groups measured once. Okay. So either of those is fine. Okay. So independent is what we have in this case because we have 2 groups measured once. 2 groups measured once. Each person is measured one time. They do the surgery and then we measure how long it takes for them to recover. What you don't want to have is some people do this one, some people do this one, and some people are in both groups. Okay. Now that's probably unlikely, right? Because it's unlikely that someone does this surgery, the standard surgery, and then comes back and does the same surgery, only they do the new surgery, right? Hopefully that's not happening, okay? But the problem there would be if the person did both surgeries and took them, a long time to recover. Well, it's probably going to take you a long time to recover. You just did 2 surgeries. It's going to throw off your results, okay? So independent means you have this sample, and there's no overlap. They're 2 completely different groups of people, okay? Dependent, on the other hand, is where you have one group and you measure that group twice. You do before and you do after, okay? So we'll see examples of that. That's what we call matched pairs, okay? So what you can't have in that case is you have someone in that group where you measure them once, but then you don't measure them a second time, okay? That's going to cause problems. That's going to throw off your results, okay? So basically, when you're testing 2 different samples, you have 2 options. You either have no overlap at all, they're 2 completely separate groups, or there's exact overlap, it's the exact same group, okay? You can't have some are in this group, some are in this group, and some are in both. Can't do that. All right, you also have to check to make sure that these 2 samples are independent of the population, okay? And that they're normal, okay? Both of them. All right, anyway, that all said, This is going to be stuff on page 266, okay? We have independent here. For part C, construct your confidence interval and state the StatCrunch path used and the result. So in chapter 10, we asked you to like show the formula and do the substitution and show the result. We're not going to have you do that here. Instead, you're going to type out or you're going to write out the StatCrunch buttons you clicked. So stat, tstats, to sample, and then did you click with data or with summary? Okay. And then, so don't forget to do that. Okay. All right. Page 565. A simple random sample of US adults embarked on a program of regular aerobic exercise. Their heart rates in beats per minute were measured before and after with the results at right. So they did the StatCrunch for us. Okay. So again, verify the requirements needed to construct this confidence interval were met. So we need to make sure that it's random. Now, so we have two different means that we're comparing. So we have the mean of the first and the mean of the second. So the question here is, are we looking at two independent samples or two dependent samples here? What do you guys think? So independent would be if I had two different samples and there's no overlap. All the people in the first group, none of them are in the second group. Dependent is where I have the same group and I measure them twice. So which one's happening here?
Dependent.
Thank you, Kara. Dependent. So we have a single group and one group measured twice. You got it, Emily. So in other words, we have a couple different people. So maybe we got like 100 people. We measure their heart rate before they start exercising, and then we measure their heart rate after they're exercising, and we're trying to see how much their heart rate goes up. Make sense? So in this case, we need to make sure that everyone that gets measured twice, we need to make sure that everyone's in both samples. What you don't want to have happen is one person gets measured before exercising and then they have to leave, or your measurement tools break down or whatever, and now you don't have their second measurement. That's not going to work, because what if that person had an abnormally high heart rate or a very low heart rate? What if they were an outlier? That's going to throw off your results, because that person might have had a low or a high heart rate to start with, but if they're in both groups, it ends up evening out. Okay, but if they're only measured once and some of the people are measured twice, your results are not going to be reliable. Okay. All right. You still also have to make sure that it's independent of the population. And norm. Okay. All right. So then fill in all of this. So they did the StatCrunch for you. So that's easy. You could just fill in that. So since this is looking at same group measured twice, this would be page 265. Okay. The steps are very similar. There's only like one or two steps that are different when you're looking at these. So let's go through these. Let's see. So page 262 is hypothesis testing for a single proportion. Okay. 263 is a hypothesis test for a single mean. So you need to pay attention to whether you have proportions or means. Page 264 is again back to proportions where you have test the difference between two independent proportions. And then page 265 is means, test for the mean of matched pairs. Matched pairs is dependent, so it's you can write right here, one group measured twice. And this one, page 266, test the difference between two independent means is two groups measured once. Okay. Page 566, question 7. In randomized double-blind clinical trials of a new vaccine, rats were randomly divided into two groups. Subjects in group 1 received a control vaccine. Subjects in group 2 received the new vaccine. Okay, so we're testing testing the difference between these two vaccines. Researchers found that 19% of the subjects in the control group had fever as a side effect, while 25% in the experimental group had fever as a side effect. So we're not testing the effectiveness of the vaccines, we're testing the side effects in this case. Okay. All right. Either way, we're looking at proportions. Okay. So remember that X is equal to your sample size times your p hat. Okay. That's how you're going to calculate this. All right. So the above situation, is that independent or dependent sampling?
Independent.
This one's independent because each group, you have rats in group 1, rats in group 2, and there's no overlap. You're not going to have any rat that's in both, because if you did, that means you're giving them both the control vaccine and the experimental vaccine. So if they get a fever, you don't know which one caused it. Okay, so you got to keep your samples either completely separate or completely the same. All right, this one's independent. Is this an example of quantitative or qualitative variables?
Qualitative.
It sounds very confident. Yes, you are correct, Kara. When we're dealing with probability, most of the time you're measuring qualitative results. Like when we were looking at M&Ms, we were looking at p hat and so on. So for red or green M&Ms, and so your data would be red or green. Okay, so you can imagine this researcher, they've got rat A and rat B, rat C. I don't know, maybe they have names, maybe they just have numbers. When they're writing down the results, they're writing down whether this rat had a fever or not. Okay. That's what they're measuring. So they're so once they've done all that, this is the column that you're going to do the probability on. You're going to count how many had a fever, and that's going to give you numbers, right? So 571 rats, 19% of them had fever, right? But this column is words. It's qualitative. Hopefully that makes sense. Anyway, is there enough evidence to support the claim that the control group has a lower proportion of fever as a side effect at the alpha 10% level of significance? Okay, so now are we looking at means or proportions? We're definitely looking at proportions here. It's not a single proportion, so I need page 264. Test the difference between two independent proportions. Okay. So we got our null hypothesis, which is going to be P1, or I guess you can write P1 and P2, or you can write the control group and the experimental group. However you want to denote them is fine. You do P1 or P2 or PCPE, okay? Now, sometimes we write it like this, okay, where it's equals zero, the difference is equal zero. Sometimes we write it like this, where we're just saying they're the same. These are the same thing, and you can write either one, okay? But in this case, I'm going to use this one because when you have a one-tailed test, I find it easier to make sure my greater than or less than is the correct direction when I have the two probabilities on the opposite side. Because the question is asking us, support the claim that the control group has a lower proportion of fever. So that would be like this, less than here, okay? If I had written it the other way, like this, P of experiment minus P of control, and I was trying to compare that to zero, if I write it in the wrong order, my less than has to switch around to a greater than, okay? So I find when you're writing out a one-tail test, it's easier to have them on opposite sides, okay? It's up to you. I mean, in StatCrunch, it's going to write it as the difference equals zero or the difference is greater than zero or whatever. So anyway, alpha in this case is 10%. Um, so most of the time when you're doing a experiment like this, you're doing a hypothesis test, most of the time the researcher wants to reject the null hypothesis. Um, that's not always the case. That's not the case here because they're testing this experimental drug. Maybe this drug is it's cheaper or it's easier to manufacture. Maybe it doesn't have to be kept super, super cold. Um, but we're not testing the effectiveness here. We're testing if it has more vaccines, right? Or sorry, more side effects. And that's a bad thing. So our null hypothesis is saying that the probability of fever side effects is the same. So there's no difference. Okay. The alternative hypothesis here is saying that the experimental drug causes more fevers, and that's a problem. So in this case, they're hoping that they don't reject the null, okay? But anyway, so this alpha, 10%, this is pretty big. Um, I wouldn't go higher than a 10% alpha, although I guess, it depends on, whether you're worried about making type 1 or type 2 errors. An alpha of 10% means you have a 10% chance of making a type 1 error. But it also means you have a much lower chance of a type 2 error. So a 10% chance of a type 1 error sounds pretty bad, but what would a type 1 error here be? A type 1 error would be where you reject the null, but the null is actually true. Well, if the null is actually true, then what that means is that the um, control group and the experimental group, so both drugs have equal chance of fever. So this new drug does not have worse side effects, but you rejected it. And when you rejected it, you secretly didn't, I mean, you didn't know the answer. So secretly, we don't even know, but secretly the fever rate is the same, but you rejected that. And so you said, oh, sorry, we believe that the experimental drug has too many side effects, and so we're not going to use it. Well, that's not a huge deal because you can just continue to use the control vaccine. Okay. Um, the flip side, a type 2 error is worse in this case. A type 2 error here would be where uh, the null hypothesis is wrong, and so this drug actually has worse side effects, but you did not reject the null hypothesis. You said, "Oh yeah, they're good. This new drug has just as many side effects as the old one, even though actually it has more." Okay. So you're then going to approve this drug for use and it's going to cause more side effects, and that's not good. So that probably is why this alpha is so high because um, it's okay to make a type 1 error here. It's not so good to make a type 2. So anyway, I know they didn't ask for us to answer any of that, so we'll we'll move on. We'll go to the next page, page 567. A researcher for Consumer Reports believes that SUVs have worse gas mileage than sedans. They gather a random sample for both types of vehicles, measure the gas mileage. All right, so they did the StatCrunch for us. So help me fill some of this out. What type of test is this? What do you think? Right or
Left-tailed.
two? Left-tailed, yes. Because it's a less than right here. Mm-hmm. How many SUVs were sampled? Overall miles per gallon for SUV equals yes, so 29. What was the average gas mileage for sedans? So sedan equals yes is 21.67. Okay. Explain why this is an example of independent sampling. So independent means you have two separate groups where there's some people, some in this group, some in this group, but there's no overlap. So can a car be both a sedan and an SUV at the same time? I guess we're not counting crossovers. So a car cannot be both, can't be in both groups. Okay. And then use the computer output to do steps 4, 5, and 6. So step 1 they already did for us. Here's our hypotheses. Step 2 is our alpha. Step 3, they already got the t-stat and the p-value for us. Okay. So we're just going to jump right into question 4 and start filling that out. So right here is our t-stat 1.507. That's this. And you're shading off to the left, right? And technically this keeps going forever. I'm just not going to make you shade forever, right? It keeps going off to the left forever. P-value is 0.0734. Okay. All right. Anyway, we'll come back to that. Last page, page 568. Company studied 2 programs for compensating its sales staff. 9 random salespeople participated in the study. In Program A, the salespeople were paid a higher salary plus a small commission for each item they sold for 6 months. Program B, the same salespeople were paid a lower salary with a larger commission for the next 6 months. The following data are the amounts sold in thousands of dollars for each salesperson on each program. So, first, we need to fill in these differences, find the differences. So 55 minus 53 is 2. 21 minus 24 is -3. So you just go through and fill those in. So some are positive, some are negative. So pay attention to that. Okay. Now the other option is you can come over here to StatCrunch. So group A is here, group B is here. So unfortunately, this is not Excel, it's not Google Sheets. So you're not going to be able to just type in, equals and then use a formula. But you could copy and paste these into Google Sheets or Excel and then do this difference there. I don't know if that would be any faster. So, so copy and then paste these. And then the formula would be you do equals this one minus this one. And then you can just copy that formula down. So it's up to you how you're done. It's not that many numbers, so. But obviously, if we had a much bigger group, if our sample size was 30, which we know we want to be bigger than 30, or actually you want to be even higher than 30, so 50 or 100, maybe it would be a lot easier to do it as a formula in a spreadsheet. Okay. All right. Um, this situation, is this independent or dependent sampling? What do you think?
Independent,
Independent, you got it. And qualitative or quantitative?
quantitative,
Independent, quantitative. Because what we're measuring is not yes and no, it's not A's and B's. We're measuring how many sales in thousands of dollars that person made. Okay. Oh, sorry. Did you say independent or dependent? Might have
independent,
might have misheard you. Um, so this is actually dependent quantitative. Um, why is this dependent? So what's happening here is you have 9 salespeople, and for the first 6 months, you're measuring them on program A. And then for the second 6 months, you're measuring them on program B, but it's the same group of people. So you're not doing, you know, these 9 salespeople and then a different group of 9 people. That would be independent. This is an example of one group measured twice. Okay. So this would actually be page 265. Okay. So where we're looking at matched pairs differences. Okay. Um, Now, again, I mentioned earlier that you want to make sure that when you're doing dependent sampling, where you have these 9 people that you're measuring, you measure the same group both times, right? Because some of these could be outliers. Like this person here, uh, for the first 6 months, they sold $55,000. Second month they sold, or second 6 months they sold 53,000. That's a lot more than this guy. This guy only sold 21,000, so he's terrible, or at least maybe this guy is amazing. So if I measured, maybe this is Jack, right? And he sold 55,000 the first 6 months. Then if he quit and he left the company and I don't have this number, I can't use his data, because if I did, it would throw off my average for not group A, for program A, because that outlier is going to pull that average up. But I don't have a similar outlier for program B, and so it's going to throw off my numbers. Okay. Okay. Anyway, so that's dependent. Okay, so we'll come back, we'll fill this in. So I'm going to stop the recording. We're going to jump back to the start, page 563. We're going to fill in what we skipped over, okay?